Hi everyone. In this video, we'll talk again about binary operations on the integers, and we'll give a little bit several more examples than in class. So let me remind you that a binary operation, which is denoted by this symbol with a plus on the circle. So a binary operation on integers is a function from the Cartesian product of z cross z, meaning the ordered pairs of integers into integers. So what that means is that it assigns to every ordered pair AB of integers a unique integer which will be denoted by A plus B. Okay, so that's the definition of a binary operation. Now, binary operation is commutative if it satisfies the property that if you take A with B, A plus B, then you get the same result as B plus A. And that has to be true for every ordered pair of integers in Z. Okay. Similarly, a binary operation is associative if we have this property here. So we have three elements now, A plus B plus C. And then to define this, since a binary operation works only for pairs, we first can take the result of B plus C and then apply to that result A. And we could also do it in the opposite order. We can take first A plus B and then add C to that. And if the results of these two things are the same, then we say that this is an associative operation. And in that case, the binary operation is associative. So the third, so that has to be true for all possible A, B's, and C's in integers. An element is called an identity. So the third important property here for a binary operation to have an identity. So an element is called an identity with respect to that particular binary operation if we have that. So it's denoted by AE. So if you add that element to any element A, you get the same thing back, you get A back, and it doesn't matter whether you add it from the right or from the left. Note that the binary operation doesn't have to be commutative. Therefore, this element adding the identity to A could be different. So from this one here, so the property of being an identity means that it doesn't matter from which side you add that apply that binary operation, the result is always going to be A. Okay, so that's the property. So if you have an identity, that means this property holds for all possible A's integer A. So here are some examples. So of course, regular addition is a binary operation. It's a binary operation because if you take any two integers, A and B, and then you just add them, then the result is still an integer, right? So that's the meaning of a binary operation. Similarly, on multiplication, if you take any two integers A and B, then their product is again an integer. So that means so multiplication is a binary operation. And similarly for subtraction, whenever you have A and B integers, then A minus B is also an integer. So that means subtraction is a binary operation. okay? On the other hand, division is not a binary operation. That's just because not for there are some integers so that if you take one and divide by the other, the result is not an integer. So for instance, if you take a to be 1 and b to be 2, then we have that a divided by b, which is 1 over 2, is not an integer. It is 0.5, so it's not an integer, and therefore it is not a binary operation. And the reason for that is if you want to be a binary operation, the property has to hold for every possible pair of integers. So if it fails just for a single pair, like in this case for 1 and 2, then it's already not a binary operation. Okay. So next, so here are some examples of what can be, well, we'll have to see if they're binary operations or not again. So in this example here, I define a function a plus b to be the square root of ab. And this is again, so this is not a binary operation. And the reason for that is, again, I can take examples of integers so that if you take their product and then take a square root, then the result would not be an integer. And again, I could take a equals 1, b equals 2, and then, so for instance, a is 1 and b is 2, then a circle plus b is square root of 1 times 2, which is square root 2, and that's not in integers, so that means this is not a binary operation, right? It's not a binary operation. Okay. So let's look at the other examples. So what can we say about these examples? Which ones are binary operations, which ones are not? So so I'll write just the answers here. So if you define the binary operation a circle plus b to be 3, then no matter what my a and b are, the result is going to be an integer. So this is indeed a binary operation. So this so this is a binary operation. Okay. So next is, so here it's written GCD, which means greatest common divisor. And we haven't talked about that, but it could be shown that this is actually an integer, but so no matter what A and B are, this expression gives you an integer, so that means the resulting thing is going to be a binary operation as well. So I'll just write here, this is a binary operation. So that's okay. So how about the next one here again? So I have b squared over a, and of course I can have an example of b and a, so that b squared over a is not an integer. And so for instance, if I take b equals a equals maybe 2 and b equals 3, then so let me just give you so let me just write it. This is not a binary operation. So, and here I'll just write take a equals 2. And for instance, I can take now b equals 1. Then I will have a plus b in this example. Now circle plus b is equal to b squared, which is 1 squared divided by 2, which is again 1/2 and is not an integer. So that means this is not a binary operation. Okay, so not a binary operation, because it's enough to fail just for one example of one pair of integers, so that the result is not a binary operation. Similarly, the next example, we have the defined this thing here, A circle B is a pair of numbers. So that means it's not just one number, it's two numbers, but then if we look at the definition of a binary operation, it says that a binary operation is a function which assigns to every ordered pair of integers A and B a unique integer, right? So there's just one integer. However, in this example here, it seems like it seems that it's defined to be not unique. So this is again not a binary operation. Okay, so this is not a binary operation. Okay, so I'll write here because not unique. Okay, and here is another example. So this is not a binary operation. And what about the last example? I have a to power b. Can I have an integer, a pair of integers a and b, so that a to power b is not an integer? And the answer is yes. If I choose, for instance, a to be a natural number, a positive number, and b negative, then the result would be not an integer. For instance, so let's take a. So for instance, I can take a to be, let's say, 2, and b I can take to be, for instance, -2. And in that case, I will have a to power b is equal to 2 to power -2. So that means it's 1 over 2 squared, which is 1/4. And again, that's not an integer. Okay, so if it fails for this particular example, that means it's not a binary operation again. So not a binary operation. So we have some examples of binary operations, some other examples of operations which are not binary operations. Actually, here I should emphasize this is not a binary operation on the integers. On the other hand, if I took natural numbers, meaning positive integers, then if I take a natural number and raise it to a positive integer, again to a natural power, then the result will be a natural number again. So that would be a binary operation. So maybe I should remark here. So remark. So here, this thing here on the natural numbers, this is a binary operation. Okay, so let's talk a little bit about some other examples. So here I have an example which can be shown, which is easily seen to be a binary operation. And I would like to see what are some of its properties. So is it commutative, is it associative, and is there an identity element? So in this case, I have that a plus b is 3 times b, which is, I'll just write that this is clearly this, yes, this is a binary operation. This is a binary operation. So that's quite easy to see because 3 times b is an integer. So 3 times b is also an integer. Next one is it commutative? So for instance, it's saying if I have a plus b, well, with this circle plus b, is that equal to B plus A for every pair of integers A and B. Well, let's see. So let's calculate the left-hand side. Left-hand side actually, let's say, is given to us, right? A plus B, circle plus B is equal to 3B. And then B plus A, if I was to do it the other way around, well, that's equal to 3A. So if this was commutative, that means the 3A here and 3B would have to be equal to each other for A and B, every A and B, and which is clearly not the case. So this is not commutative. Another way of doing this is to give one example for which this equality is not satisfied. So for instance, I can say that if I take A and B to be A equals, let's take example here. Example, A equals 1, B equals 2. Then we have A circle B is equal to, well, it's 1 circle 2, and that's equal 3 times the second number, which is 3 times 2, which is 6. And on the other hand, B plus A is equal to 2 circle 1, which is 3 times, again, the last number here, which is 1, so that's 3, and 3 is not equal to 1, so that means this is not commutative. Okay, so I just needed one example to show that this is not a commutative operation. Okay, so next is this associative? And again, so what does that mean? That means we want to know if it's true that, so let me just write the answer here. This is not commutative. Okay, so next we want to know if it's associative. And to do that, we have to check if we have that A plus B plus C is equal to A plus B, then plus C. Okay. So to do that, again, so remember, we should remember what this operation, how it's defined. So it's defined here, 3 times B, right? So if I apply it to right-hand side on the left-hand side, I again will get different now answers, as we can see. So so let's take the left-hand side, for instance. I'll have A plus B plus C. Well, actually, let's do it like this. First, let's consider B plus C. And with that notation, with our definition, we get that this is equal to 3 times the second number, which is C. And then I need to do A plus B plus C. Well, since B plus C is equal to 3 times C, and this is A plus 3C, right? Which means that it's equal to 3 times the second thing here, which is 3C, so it's 9C, okay? So that would be the result of doing this. And on the other hand, if I do A plus B, well, plus C, then I will have that this is equal to, so a plus b itself is 3b. And then I add to that c. And no matter what my first element is, the result is going to be 3 times c. So that would be my right-hand side, and this thing here would be my left-hand side. So that means 9c would have to be equal to 3c, and that would only happen if c is equal to 0. So that means in general, this doesn't hold. So for instance, I could have taken c to be 1, and that would give me a counterexample to the associative rule. So for instance, so this is again an example of something. So it's not commutative. Okay, so it's not commutative. So another way of doing this, so we saw the right-hand side and left-hand side give me different expressions, so they're not equal to each other. So that means it's not commutative. Another way of doing it is just by taking an example, and the one example could be so for instance, let's move this a little bit down. So here you can just take, so another way to see that it's not commutative is to take, maybe let's take a equals 1, b, actually let's take a equals b equals c equals 1. So if I do that, then from what I have, I will have that a plus b plus c is equal to 9 times c, which is 9 times 1, which is 9. But a plus b plus c would be equal to 3 times c, which is 3 times 1, which is 3. So these two things are not equal to each other. So that means the result is not, sorry, I was to say here, not associative, not associative. Okay, so the associativity fails as well. Okay, the next thing would be to see if there is an identity element. So if there was an identity element, then I would have to satisfy the property that, so if, so let's just say, the question is there an element e in the integers such that if I take a circle plus e, I get a back, and moreover, if I take e and I circle plus a, I get a as well. Okay. Well, it's easy to see that this is also false, so there is no identity element for this operation. So I will leave this to you as an exercise, but the idea would be to see that, well, what is this? This is just 3 times e. So if 3 times e equals a, then well, the appropriate e is, for instance, if a is equal to 1, that means there is e would have to be 1/3, so that couldn't be an integer. And similarly, if you take this one here, this would also fail. So so this would basically say there is neither right inverse nor the right identity nor Well, so let's just say that there is no identity. Okay, so I'll leave this to you to work on. Okay, so let's do well, so let's talk about what's called closed sets, which are closed under binary operations. So we talked about this in class. So recall that a subset of the integers is called closed under a binary operation. Yeah, if for every two elements in B in that subset, we have that the result of the operation is also in there. Okay, so if you take, for instance, the operation to be the regular addition or regular multiplication, then if you take two even integers, then the resulting thing would still be in, well, 2z would be closed under both of those operations, because if you take two even integers, you add them, the result is still even, and if you multiply them, the result is still even. On the other hand, if you take odd integers, this is not the case anymore. So for, well, at least in the case of addition, so if you take odd integers, let's take 3 and 3 again, then if you add them, you get 6, so that's not an odd integer anymore. So odd integers are not closed, they're not closed under addition, okay? However, they are closed under multiplication. If you take two odd integers, the resulting thing would still be an odd integer, okay? So this is where I'll stop talking about binary operations. The next video will be on section 1.3.